I had the pleasure to interview Dr. Guillermo García Segura, a Spanish astronomer now working in Ensenada, Baja California, Mexico, specializing in the theoretical study of the magnetohydrodynamics of gases ejected by stars, either violently as supernova explosions or relatively energetically such as stellar winds. In particular, he studies the formation of nebulae around stars, such as the spectacular and colorful planetary nebula NGC 1514, recently observed by the James Webb Space Telescope.
Well, I'm professor in the Institute of Astronomy in Ensenada, Baja California. I arrived to Mexico in 95 and to Ensenada at the end of 97, so I have been there 30 years already in Mexico.
Guillermo, originally from Malaga, Spain, later embarked on an inspiring academic journey by completing a physics degree at the University of Granada. He then followed with a master's and a doctorate in astrophysics in the Canary Islands, turning his childhood dream to become an astronomer into reality.
Well, I studied physics in Granada and then later in the Canary Islands. And then I decided to do the PhD in the Canary Islands, but my thesis work, I decided to do my thesis work in the University of Illinois at Urbana-Champaign. And I met there Jo Chu. She told me that we need to do new model for Wolf-Rayet nebulae. So she introduced me to Mordecai Mark McLeod, which is in New York, Natural History Museum. I started with him working theory in nebulae, first analytically, and then I discovered the numerical simulations at the NCSA. And I said, "Wow, this is my opportunity." I enjoy a lot. I love to do all the simulations, all the movies, and so on. So I really enjoy, and I have been doing that for my whole life now.
In the interview, Guillermo highlights how important it is to meet people working on your field. While presenting his work at one meeting, he got the attention of the then director of the Instituto de Astronomía at the Universidad Autónoma de México in Mexico City, opening the door for now a lifelong position in Mexico.
In the Wolf-Rayet meeting in Elba in Italy, I met there Gloria Koenigsberger. She was the director of Mexico. And she said to me, "What are you going to do after the PhD?" I said, "Well, why you don't come to Mexico? We just got a postdoc for you." I said, "Okay, send me your CV. I will." I said, "Okay, I'll be there." Well, I knew that the School of Interstellar Medium in Mexico was great, so it was an adventure, but not so much scientifically speaking.
How did you started to study astronomy? I mean, that's something that you knew for a long time that you wanted to study?
Yeah, when I was a child, I enjoy a lot talking with my father. He liked it a lot, astronomy also. He had a small sailing boat. The name was Andromeda. So we were very excited about constellation, Greek mythology, and things like that. After that, when I was a teenager, more or less 14, 15 years old, I met the people of the Astronomical Association in Malaga. And then at the same time was the Cosmos, the Carl Sagan. It was great for me at that time. I said, "This is what I want to study." And then from then up to now.
Regarding the work that you do, we are very used to the beautiful images from the Hubble, James Webb Telescope. Everybody gets excited about that, but not all the astronomers are working in taking those images. Many astronomers like you rather try to explain what the images are telling us. Could you explain why it is important that astronomers do that?
Yeah, for me, the key is the time, because when you see a picture from a telescope, you have a frozen image in time. But with numerical simulation, you can go back, put your ingredients to make a nebula and evolve it in time and see what's happening at the end. So it's very, very interesting, because it's the only way that you really can prove that you get this kind of shape what is the origin for the shape? What is the physical origin? And the only way to see that on time is artificially with numerical simulation. So it's a whole new, like another dimension, playing with time.
Right, but you need to understand the physics behind.
Right, of course. Everything is physics here. It's fluid dynamics, gas dynamics.
But one of the things that motivated me to talk to you is when I heard that the people that observe this beautiful image of NGC 1514, they talk about your models and they talk about one of them. It is model A4. Can you explain how this model explains the shape of this planetary nebula?
Yeah, the idea is not new. I mean, many people have worked in the fusion of stars. It's called the common envelope evolution, when one star gets a red giant star and then is so close to the secondary star that literally the secondary goes inside, making a spiral. And then at the end, the two cores get very close. It's a close binary. And the envelope is ejected. This is an old story, but there was no numerical simulations and realistic models. And for the first time, we did this kind of models, and we really got this kind of nebulae. I mean, the result. No?
And a question, knowing about planetary nebulas, that it is the last stages of the life of a star. Usually the one star expels the material, but in here you're saying that it is not necessarily the end stage in the life of a star, but rather the interaction that force this ejection of material?
Exactly. Classically, a planetary nebulae is a red giant that ejects mass slowly, and then when you get the naked core, then you have a wind and a photoionization that produce the nebula. But in the binary scenario, this happens much faster. The secondary star goes inside the primary, do a spiraling. The ejection is made in 300, 400 days only. It's very, very quick.
Mm.
And then after that, you still have both stars. You can have accretion disk. You can form jets. Many interesting physics. You produce the planetary nebulae in another completely different way than the classical view.
I didn't know, but it's good to talk to you about that. So you model this type of interaction. So you also model the evolution of one star. Do you also model that?
Sure. Yes. First, we model with a single star, and then you arrive at the conclusion it's impossible to explain this kind of nebulae. And then introducing the secondary star, you can have much more freedom to produce this kind of things, but it's more difficult.
Guillermo produces many models, so we ask him, is this the only one that can explain NGC 1514?
There are several models that can explain the nebula, but I mean, this kind of rings is quite common. I mean, not quite common, but there are a few nebula that have this kind of rings. Even for massive stars, there is another case, supernova 1987A, has this famous picture of two external rings and another ring inside close to the star. It's also a product of common envelope evolution. So actually, this is it's a field that is really now in fashion, because all the detection of gravitational waves from black holes merging, neutron star mergings, and so on, is coming from the same physics. Has to be a common envelope evolution of two massive stars. The only difference with planetary nebulae is that we can see the product. I mean, the outcome, the nebula that come from the common envelope evolution. And in the other cases of black hole or extragalactic sources, you don't see anything, of course. So studying planetary nebulae and the fusion of stars is very interesting also to understand the process itself for all kinds of masses. Actually, I will say that planetary nebulae now is the best object to study common envelope evolution, because at the end you see the result how the mass has been ejected, how are the binaries, how close the binaries are, and so on. You have all the information. And in the LIGO, or other kind of detection, you don't see anything, just the gravitational wave.
Because theoretical studies require developing precise numerical models, Guillermo and his team use powerful supercomputers to run models of supersonic shock waves, some of which can take days to run. So now let me ask you, what kind of projects you are working on now?
Right now, I am involved in the calculation of the neutral spikes that you can observe with James Webb Telescope in several planetary nebulae. For example, the first one observed, the Southern Ring Nebula or the Ring Nebula, both has this tiny, long neutral spike that you observe in the molecular hydrogen filters. And my models are already explaining the formation of these long, thin spikes, which is, I think, it's very interesting also.
Yeah, well, I'm looking forward to read about that because I'm sure that it is very interesting just to understand a lot of what is going on in this subject. So, and now that you are in Ensenada, you also make wines, right?
That's right. I have a small vineyard and I produce my own wine, and it's a great hobby.
And what is the name of your vineyard?
La Milagrosa.
Oh, so good. So one of these days I will go to visit and try. I'm sure your wines are delicious. I love wine and I'm sure I will love to try them.
Many astronomers have already tried my wine.
Oh, that's good. That's great. That's wonderful. So congratulations for that.
Thank you, thank you.
Well, thank you so much for this interview and also explaining, I mean, much more than I expected. I mean, I learned a bunch by talking to you, and that is great that you are creating those models that help us to understand the beautiful images that we are looking at.
Thank you to you.